Hello, my name is Ignacio Vigers, and this is the presentation of my project for class me510. The main topic is the modeling of energy use via the Gini coefficient. A secondary goal is to show decomposition analysis for a set of 7 or 8 countries. Originally, the intention was to do the decomposition for 8 countries, but because of data issues, one of these had to be removed from that section of the project. The plan of my presentation is as follows. First, I will provide a background and formulate a thesis based on the theory of economics, and the aim will be to assess the extent of agreement between theory and practice in the form of real data. This data comprises information from 8 countries, and it will require filtering and also a preliminary inspection to assess the adequacy for further statistical analysis. Here there's a difference between filtering and cleanup. In filtering, we remove observations where the value of a variable does not seem feasible, or the value looks questionable. Whereas in cleanup, we are allowed to keep the data after making an adjustment, which could come from expert knowledge, or an educated guess, or an interpolation from other observations. In this research, there's no cleanup, and we just do filtering of suspicious data. The main statistical tool in this research is the linear regression analysis, and after running some regressions, we are going to recommend a model for linking the fluctuations in the Gini coefficient to changes in the energy use. Now, it should be emphasized that this link is by no means a cause-effect aspect. As you know, linear regressions don't provide the cause-effect relation between predictor and response variables. Once we are done with the regression part, we'll switch gears to the decomposition analysis, and we'll end up with conclusions. The Gini coefficient is well known in economics, and it was devised by the economist and mathematician Corrado Gini from Italy. He was born in the late 19th century and died in 1965. He was also interested in demographics, and as a matter of fact, the Gini coefficient links demographics with economics. Broadly speaking, the Gini coefficient is used as a measure of how evenly wealth is distributed in an economy. Typically, for economy, we mean a country, although it might be defined with the granularity of a region or a province. To better understand the concept of Gini coefficient, let's look at this graph. Here, the horizontal axis represents the percentage of a population, whereas the vertical axis represents the percentage of total wealth in that country. The curve below the straight line is called the Lorentz curve. Thus, for each percentage of the population, The Lorenz curve indicates what percentage of wealth is in possession of that sector. For instance, in the origin, the interpretation is that 0% of population possess 0% of the wealth. Likewise, the upper right extreme means that the entire wealth is distributed among the entire population in some way or other. It doesn't mean equitative distribution. In fact, the equitative distribution of wealth will be represented by the straight line that connects these two extremes. In real life, we'll never see a perfectly distributed wealth. We will see more the Lorenz curve rather than the straight lines. The Gini coefficient is a ratio of two areas. The yellow area divided by the area of the triangle. In an economy where most of the wealth is concentrated in a small sector of the population, the yellow section would be most of the triangle, whereas in a communist country, for example, the yellow section will be small or non-existent. This is because supposedly in a communist economy, most of the basically all the wealth is property of the entire population in equal parts. Aside from the social aspect, the concept of Gini coefficient is by itself interesting, as it might reveal information on variables and impacts relevant in the design of energy policies. The context of this research is the use of energy as a normal good. And by that we mean that when we have more income, we tend to use more energy. As an example, for fun activities or vacations, we spend more money in fuel or in playing equipment. However, the law of diminishing marginal utility states that if our income increases, even though the energy use will also increase, it will be at a lower pace than our income growth. People under the poverty line will increase their energy use pretty much at par with their income growth. But as the individual gets more, as he gets higher and higher income, he is less likely to spend extra income on energy. As people below the poverty line get a higher income, we can think of it as the Gini coefficient being lower, as that means that the total wealth is being distributed more evenly. With that background, we can formulate the thesis that the Gini coefficient and the energy use per capita are negatively correlated. And this is what we will try to confront with the real data. The data set for our analysis is built with two major criteria. One is the availability of sufficient and well-behaved data, and the other criterion is that these countries be from Eastern Europe or Latin America, and also one country from the Caucasus. The reason for selecting economies from these political geographies is that during the 80s and the 90s, all these economies underwent at different times transition from state-controlled economies to a free market environment. No, not every country started at the same time, and not every country attained the same degree of market freedom. However, that transition gives room to fluctuations in the Gini coefficient, which we need for analyzing movements in the energy use. The countries in our sample are Argentina, Belarus, Brazil, Georgia, Peru, Poland, Romania, and Ukraine. Before any reliable result can be expected from our analysis, it is important to glance at the data and check for observations that seem abnormal, as well as removing records with missing values. We want to identify suspicious data, and the concept of the Gini coefficient is useful because from its meaning we can infer that there will be no abrupt changes in the Gini coefficient, as that will mean strong shocks in an economy. For example, wars or the exodus of a small sector with all the wealth will certainly cause a sharp change in the Gini coefficient. However, in some of the samples or in some of the time series gotten for these analysis, there were quick reversals which, for purposes of the Gini coefficient, don't make sense or don't seem legitimate or reasonable. Case in point, let's look at the time series for Peru. As we can see, there's missing data for almost 2 decades, or more specifically for a decade and a half. And in 1896, as well as in 1986 and 1994, there are 2 values, but they are surrounded by missing observations. So there's no way to compare with neighboring records whether these observations are legitimate or will be an anomaly in linear regression. There being no way to compare these observations, it's decided that we should remove them. Likewise, in 1997, the Gini coefficient is substantially lower than the following values, and a shock of that magnitude seems unlikely. In Peru, there was a crisis, but it will not entail such a shock in the Gini coefficient. There was no revolution or no war, so it was decided to remove that observation as well. And from 98 onwards, we can see how the values of Gini coefficient show more stability. Argentina is another example. Here we already removed the missing observations, and even though we can see a sharp increase in 1995, those observations seem legitimate because for the following years the range of Gini coefficient seems stable. Going forward to later years, we see how the trend goes down. Brazil exemplifies an even more stable trend in the Gini coefficient. For several years it stays in the range of upper 50s or 61 in the Gini coefficient, and then it starts a downward trend. As for the preliminary inspections, it's illustrative to look at the time series for some countries, and in this case we see the case of Peru, where the Gini coefficient follows a downward trend at the same time that the energy use follows an upward trend. Here the GDP growth seems to coincide to some extent with the trend in energy use. However, this is an exception. In other countries there is no discernible relation between GDP and energy use or the Gini coefficient. Let's look at the time series for Brazil. Here again we see a negative relation between the trends of the Gini coefficient and the energy use, but there's no discernible relation of any of these two variables with the GDP growth. The case of Poland is another example where there's no discernible relation with GDP, and even the relation between the Gini coefficient and energy use seems more diffuse. That diversity of trends from the visual inspection motivates us to run the regression analysis to try to quantify how good is the fit of the Gini coefficient as a predictor of the energy use. The first regression we are running is a linear model with only one predictor, and it being the Gini coefficient, and as a response variable we use the energy use per capita. The regression gives this result a negative beta, which is in line with our thesis of negative correlation between the predictor and the response. And the adjusted R square is a good indication of how well it's the Gini coefficient fitting or predicting the response variable. Other than the sign of the beta parameter, there's little else to infer from the magnitude of beta. This is for two reasons. First, the Gini coefficient is defined in percentual terms, whereas the energy use per capita is the kilograms of oil equivalent for each person. Another challenge in interpreting the magnitude of the beta parameter is that the variables can be transformed or scaled. So by multiplying the predictor by some constant, we might be able to manipulate the beta parameter. This is why we should not draw conclusions from just the magnitude of beta as to determining the strength of the correlation. At this point, the regression is of a static nature. That is, it is not involving changes in the variables, but we are interested in modeling the fluctuations of the response from fluctuations in the predictor. This is why we move to the next step and run a regression analysis of changes in the predictor to changes in the response variable. Now here the predictor is the delta in Gini coefficient, and the response variable is the logarithm of the ratio of two consecutive values of energy use. The logarithm smoothens the observations and also gives us a rate of growth, which is what we are interested, as that makes the response variable dimensionless and now more comparable to the predictor variable, which is also in percent terms and dimensionless. From the results of the regression, we see that even though the beta parameter has a negative sign, the magnitude is very small. So the negativity of, or the negative sign of beta is it's questionable in that it might be just a matter of luck, or it might be a random fact. Additionally, the adjusted R-square is very low, and that doesn't convey a robust or reliable fit. In fact, if we see the scatter plot of changes in each of the predictor and response variables, we see how sparse the observations are, and there's no discernible linear relation between these two variables. So we need to devise other variables on which to run the regression. After trying several transformations of the predictor and the response variables, I came up with a model that takes us very closely to the results we got from for the static case. This regression uses two predictors which are based on the Gini coefficient. Here we are interested not only in the current Gini coefficient, but also in the ratio, or in the rate of growth compared to the initial value of Gini coefficient for each specific country. Likewise, we are interested in the response as a rate of growth between the current energy use compared to the initial energy use of that country. Now, we are interested in the beta 1 and beta 2 parameters. The beta 1 parameter is it helps customizing, so to speak, the it helps customizing for a specific country, and the beta 2 parameter is properly the variable that reflects the changes in the predictor. This is this resembles the example we saw in class of a time series where we saw the regression of the current state using observations from prior periods, except that here they are expressed as a single variable in the form of a logarithmic ratio. The negative sign of beta 2 confirms the thesis of negative correlation between the Gini coefficient and the energy use. Running the regression with only one parameter, or basically ignoring the predictor x1, we will get a beta 2 of minus 1.2, which means higher sensitivity of the response to changes in the predictor. However, the adjusted R-square for that scenario was 41%. So I opted to include the two predictors and get the higher adjusted R-square. And as we can see from the p-value, this regression can be considered reliable. A further validation of this model is obtained by looking at the theoretical and sample quantiles, and we can see that except for large values, it matches the normal distribution, or they are, so to speak, hand in hand, the sample and the theoretical quantiles. With this, the recommended model is the predictor, the model using two predictors to model the changes in the energy use. On the topic of decomposition analysis, the information or the records used were retrieved from the US Energy Information Administration, which has data for energy intensity and the variables that we need for defining the structural effects, as well as the GDP growth or the GDP level. This gives this table for the composition analysis, and the country that was eliminated from the sample is Ukraine, because as we can see from the structure table, all the values are above 1, which doesn't make sense since the energy sector is a subset of the entire economy. Therefore, it is not reasonable to exceed 1. As we plug the numbers in the formulas for decomposition factors or factor analysis, we see that with the exception of Georgia and Romania, the activity effect has increased by factors of 4 or even greater. Very likely this is common to almost all the countries in the world. The few exceptions might be those countries that remain isolated or with an economy that hasn't been modernized. Also, the intensity effect factor reflects growing efficiency of the energy sector, with the exception of Georgia and notoriously Brazil. Since Brazil is emerging as a leader in the world economy, it seems that Brazil needs to modernize its energy production. Now, the share of Brazil's energy sector appears to be perfectly proportional to the overall economic activity. This raises suspicions as to the measurements of these variables. I find it hard to believe that the economy and the energy sector in Brazil grow exactly at the same pace or move in the same direction and the same rate. So this might suggest a need to scrutinize the accuracy of the surveillance. As a conclusion, even though the Gini coefficient has a long-term character versus the consumption of energy, which is short-term in nature, we saw how the Gini coefficient in its cumulative development exhibit a remarkably high explanatory ability on the fluctuation of the energy use per capita. The strong reliance of other goods and economic variables on the access to energy suggests that many of these results may be qualitatively similar to other contexts. This report showed how the Gini coefficient is useful for quantitative analysis, and therefore, in light of its proven benefit, it is desirable that all the countries sustain a standard effort in keeping up with the estimates of the Gini coefficient, especially as we are interested in defining or designing energy policies. Thanks for your time.